Okay, hey there, Math 2150. So this video is getting us ready for 3.3. 3.3 is the only lesson that I want you to cover this week. However, if we were in a traditional face-to-face class, I would spend at least one day doing a pre-calculus review just because my math lab expects you to remember how to find vertical asymptotes and how to find horizontal asymptotes. And from experience, usually my calculus students don't remember how to do that. And so we spend an entire day kind of just doing a little bit of pre-cal review. That way you can be successful in 3.3, okay? So to start off, I'm going to make sure you realize in 3.3, we're using the first and the second derivative test. Okay, so that hasn't gone anywhere. But we're using the first and second derivative test on rational functions, okay? And so that's what makes it more challenging, the rational function part. So that's the whole idea behind 3.3 is to use the first and second derivative on rational functions. But anyways, I should first off give you the definition of a rational function. And a rational function, the definition technically is the ratio of two polynomial functions, okay? And so let me give you some examples because examples make more sense a lot of times than definitions in my opinion. So an example, f of x equals 1 over x. Guys, that is the most simple rational function there is. It's technically a rational function because there's a variable located in the denominator. That's pretty much the key. If there's a variable in the denominator, it is a rational function. Here's another one. G of x equals x squared over x plus 4. Like that is also a rational function. So there's two examples of rational functions, okay? And so when you have rational functions, there are a couple of things that we're going to talk about in this review. I need you to be able to find holes. I need you to be able to find vertical asymptotes. I need you to be able to find horizontal asymptotes. And I need you to be able to find slant asymptotes, okay? And I need you to be able to find x-intercepts and y-intercepts. And I'm not sure if we know how to do some of this kind of stuff. So that is the main goal of this little pre-cal review. And so it's a lot, just to warn you. So let's get started with some of it, okay? I'm actually going to start with an x-intercept. So I've told y'all this before in class, but I'm going to tell you again. Like this point right here, that's an x-intercept. This point right here, that's an x-intercept. This point right here, guys, is 1, 0. This point right here, guys, is negative 1, 0. It's easy to see that x-intercepts mean y equals 0. Okay, so if you ever want to find an x-intercept, you set y equal to 0. Okay, big idea. If I come over here and do another little graph, y-intercept, so that's a y-intercept. That point is 0, 1. That's a y-intercept. That point is 0, negative 2. Well, again, it's really easy to see that y-intercepts mean x equals 0. So there's two big ideas for you, okay? Real quickly, if I give you an example that says find the intercepts. If it says intercepts, guys, that means you need to find the x and the y intercepts. Okay, find intercepts. And let's let f of x equal, I don't know, 2 over x plus 3. Trying to make it simple. Okay, so again, an x-intercept means y equals 0. And some of you may say, Ms. Floyd, I don't see a y in that problem. That's f of x equals 2 over x plus 3. But guys, f of x and y are treated similarly. So f of x would be 0 equals 2 over x plus 3. And when I have a number equals a fraction, I like to put the number over 1 and set it up as a proportion. So if you were to cross multiply, guys, 0 times x plus 3 is 0. And 2 times 1 is 2. So you get 0 equals 2. 0 does not equal 2, guys. And so what does that mean? As weird as this is, and I did this on purpose so you would understand, the x-intercept, there isn't one, which means this graph will never cross the x-axis. Okay, it does not touch the x-axis, so there are no x-intercepts. If we do the y-intercept, guys, again, the y-intercept means x equals 0. So everywhere we send x, we're going to plug in 0. So that'll be 2 over, there's an x. Oh, God, that's 0 plus 3, which will be 2 over 3. So the y-intercept would be x is 0, y is 2 over 3. So that right there would be the y-intercept. Okay? And again, that's a pre-cal review kind of question, but all of this is going to be pre-cal review. So if you already know that, great. Okay? The next big idea that I wanted to talk about, was holes. Okay? And I need to give you some notes on holes. First off, some of you are like, what the heck is a hole? So if I draw a graph and I draw like a parabola, but then there's literally a hole out of the parabola. And the thing about holes, guys, if you graph this in y equals in your calculator is not going to identify a hole. So like there's no way around this. You have to know how to find a hole. And like this point right here, that is the hole. Okay? It's literally a point that is missing. And so you may say, well, how do you find holes? Holes occur when the same factor is located in the top and the bottom. And what I mean the top and the bottom, let me use better math words, located in the numerator and the denominator of our rational function. Okay? And so they're very, very rare. Like holes are very, very rare. Why are they very, very rare? Because the same factor has to be located in the numerator and in the denominator. So that's why you might have gotten out of high school without ever even hearing about them. So now that you know when they occur, you should say, okay, so if the same factor is in the numerator and the denominator, so how do I know what the hole is? You simply set the same factor, whatever that factor is that's in the top and the bottom, you set that factor equal to 0. Okay? And so let me give you an example. And I'm going to say find the hole. Okay? Find the hole. And that would be if possible. Or if it exists. If it exists. If it exists, because again, very, very rarely do they exist. Okay? So f of x equals, let's say, x squared plus 6x plus 9 over, let's do x squared plus 5x plus 6. Okay? Deliberately design this, so let's take a look. X squared plus 6x plus 9 and x squared plus 5x plus 6. Both of those quadratics can be factored. So if I factor the numerator, guys, and if I factor the denominator, so I need numbers that multiply to get 9 and add to get 6. So hopefully you realize that's x plus 3 and x plus 3. That's how the numerator factors. And the denominator, I need numbers that multiply to get 6 and add to get 5. So that's going to be x plus 3 and x plus 2. And so when I designed this 2 seconds ago, I said, oh, look, x plus 3 is located in the top and the bottom. And so we have a hole. The same factor is located in the numerator and in the denominator. So I'm going to set x plus 3 equal to 0 and simply subtract 3 on both sides. So x equals negative 3. And some kids think they're done, and you're not. because that's why I drew you a picture. If I go back up here to this picture, that's your hole. Your hole is not an X value. Your hole is literally a point that is missing, okay? It is a point. It is a missing point. And you and I both know that points have X values, but they also have Y values. So now we need to get the Y value, okay? And so we need to simply plug back in -3 to my function. But guys, if you plug in after you simplify. So if I have an X plus 3 and an X plus 3, if you divide X plus 3 and X plus 3, these X plus 3s are going to cross out. You got it? Or cancel out, divide out. And so what do you have left? You have f of X equals X plus 3 over X plus 2. And what was X? X was -3. So it'll be -3 plus 3 over -3 plus 2, which will be 0 over -1. And 0 divided by -1 is simply 0. So Y equals 0. And so what's the ordered pair? -3, 0 is my hole. Okay, so that's how we find holes. Next, vertical asymptotes. Okay. You're going to see me, when I do the notes, just do the VA to mean vertical asymptotes and understand the shorthand. A vertical asymptote, guys, Lord, you can see how crooked my lines are, okay? A vertical asymptote is something like this. And again, you can't see a vertical asymptote when graphing. This red line technically doesn't exist. But what happens is the function, let's do the function in like blue. The function approaches this vertical asymptote, but it doesn't actually touch the vertical asymptote. So it's going to get really freaking close, but it doesn't actually touch the vertical asymptote. And so that's what a vertical asymptote looks like. This vertical asymptote here would be actually at 1, 2. So that's X equals -2. That's where that vertical asymptote exists, okay? So your question should be, how do I find vertical asymptotes? Well, you set the denominator equal to 0. It's that simple. Set the denominator equal to 0. That's how you find a vertical asymptote. So if I go back to the problem that I just gave you, the problem that I just gave you was f of X equaled X squared plus 6X plus 9 over X squared plus, 5X? Yeah, 5X plus 6. So I just gave you this problem, guys. And so what do you need to do? Before you check for vertical asymptotes, guys, you have to check for holes. And so how do we find holes? We factor the numerator and we factor the denominator. That's why I taught you hole first, because I want you to find the holes first when doing these problems. After you find the hole, I then want you to go find the vertical asymptote, okay? So when you factored this thing just a minute ago, we got X plus 3 times X plus 3 over X plus 3 times X plus 2. Okay, that's what we got just a second ago. The X plus 3's canceled because those were the hole. Okay, that's where the hole was. And so what is left in the denominator? The denominator is simply X plus 2. Okay, and so we set X plus 2 equal to 0. And when we set X plus 2 equal to 0, we subtract 2 on both sides. And again, X equals a -2. That is your vertical asymptote. So actually, I should write that the other way. I should say vertical asymptote at X equals -2. Okay, so let me give you one more example of this. What if I have G of X and I let it be X squared plus 6X plus 8 over X squared plus 9X plus 18. Okay, So if you factor the numerator and if you factor the denominator, so if you simplify this rational function, if you simplify it, you're going to get x plus 4 and x plus 2. Hopefully you know that 4 times 2 is 8 and 4 plus 2 is 6, so we have factored it correctly. In the denominator, I'm going to get x plus 6 and x plus 3. Why? 6 times 3 is 18 and 6 plus 3 is 9, so we have factored correctly. If you take a look at this, guys, the same factor is not located in the numerator nor in the denominator. And so if I was asking you for wholes, you would say wholes, none. There are no wholes because no factor is located in the numerator and in the denominator. So vertical asymptotes still exist because vertical asymptotes occur when you set the denominator equal to 0. And this time we have two factors, so we're going to set both of them equal to 0. So if we subtract 6, we get x equals negative 6. And if we subtract 3, we get x equals a negative 3. And so, guys, this time we have two vertical asymptotes. We have one vertical asymptote at negative 6, and we have one vertical asymptote at negative 3. Okay? And you may say, well, why aren't we going back to get an ordered pair? Like, why is this not an ordered pair? Because, guys, a vertical asymptote is this red line, and it's actually a vertical line, okay, that red line. And so if you remember back from Algebra 1, x equals a number was a vertical line. And so this is literally the equation for a vertical line, which is your vertical asymptote. Okay, so those first two. Next one is the horizontal asymptote. Okay, horizontal asymptote. And you guessed it, I shorthand that one for HA. Okay, and if I draw you a little graph again, because usually, guys, you see vertical asymptotes and horizontal asymptotes. So let me draw in a vertical asymptote. And let me also draw in a horizontal asymptote. And so a graph similar to this could be like this. Okay. See how the graph is getting closer and closer to the vertical asymptotes, but it's also getting closer and closer to the horizontal asymptotes. So if you want to be specific here, so you can see, we have a vertical asymptote at x equals 1, and we have a horizontal asymptote at y equals 2. Okay, so there is some basic notes, and there are 3 scenarios I need you to memorize. Okay, so horizontal asymptotes, there are 3 scenarios how we figure out if there's a horizontal asymptote. Scenario 1, the degree of the numerator is greater than the degree of the denominator. And some of you are looking at me on this screen and you're thinking, degree? What the heck is degree? Degree is the highest exponent, guys. So when I say the degree of the numerator, I'm saying what's the highest exponent of the numerator and the highest exponent of the denominator. And if the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote, period. So let me give you an example of this. F of x equals x squared plus 3 over x. Okay, so the degree of the numerator, guys, is 2 because the biggest exponent is 2. The degree of the denominator is an imaginary 1. Okay, so take a look. It's bigger on top than it is on the bottom. So what's the answer? There is no horizontal asymptote in that first example. Okay, so if it's bigger on top, it's easy. There isn't a horizontal asymptote. So what happens if we flip-flop it? What happens if the degree of the numerator is less than the degree of the denominator? Okay, and if the degree of the numerator is is less than the degree of the denominator, then we do have a horizontal asymptote. And the horizontal asymptote is at y equals 0 every single time. Horizontal asymptote is at y equals 0 if the degree is smaller on top than it is on the bottom. So let me give you an example of this one for you, gang. Let's do g of x equals 2 over x cubed plus 4. Okay, so the degree of the numerator. So some of you are like, okay, I don't know what the degree of the numerator is. The degree of the numerator is actually 0. And the reason is 0 is because 2 is a constant. So the degree of constants is 0. Okay, the degree of the denominator is clearly 3 because the biggest exponent is 3. So obviously the denominator's degree is larger than the numerator's degree. And so there is a horizontal asymptote at y equals 0 for that problem. Okay. And last scenario. So you guessed it. I talked about the numerator is bigger than the denominator. And then the numerator's degree is smaller than the denominator's. And so the last scenario is when the degree of the numerator is equal to the degree of the denominator. Okay. And so there is a horizontal asymptote at these problems. There's a horizontal asymptote at y equals the leading coefficient of the numerator, I'm shorthanding because I'm running out of room, of the numerator divided by the leading coefficient of the denominator. So, last example for horizontal asymptotes then. Example, what if I said h of x equals, let's do the problem we talked about earlier. X squared plus 6x plus 9 over x squared plus 5x plus 6. We did this one earlier. And so if I talk about the degree of the numerator is 2 because the highest exponent is 2. The degree of the denominator is also 2 because the highest exponent is 2. So the degree of the numerator is 2, the degree of the denominator is 2, which means the degrees are the same. So the horizontal asymptote is at y equals the leading coefficient of the numerator. So what's the leading coefficient here? An imaginary 1 divided by the leading coefficient of the denominator, which is another imaginary 1. And 1 divided by 1 is simply 1. So the horizontal asymptote would be at y equals 1. Okay, so that's your horizontal asymptote notes. I got one more type of asymptote to teach you. And if we were doing this in class, this would take a whole day to do all of this stuff. So the last one is a slant asymptote. And honestly, you probably got out of high school without ever hearing about a slant asymptote as well. That's called SA. That's what I call it, at least. It's for shorthand. So a slant asymptote, they're very, very, very rare. They occur only if the degree of the numerator is greater than the degree of the denominator by exactly 1. Okay, so it has to be bigger on top than it is on bottom by 1 degree. Okay, so that's when they occur. So now that we know when they occur, you should say, Ms. Floyd, so how do we find them? And this is where I usually get kids that are lost. Use synthetic, and y'all know I'm not the best speller, so I might have messed that up. Use synthetic division to to find slant asymptote. Okay, so let me give you an example, because some of you probably don't remember what synthetic division is either. Okay, so an example. Find slant asymptote. And if you haven't looked at the homework, the 3.3 homework, several problems on the actual homework assignment on my math lab is problems like just find the whole, or just find the vertical asymptote, or just find the horizontal or slant asymptote. So this little pre-cal review can answer about half the questions on my math lab for you, just in case you were looking or you're wondering. F of x equals, let's do x squared. No, let's do 3x squared plus 9x plus 1. I'm just making something up, guys. Over x plus 2. Okay, so if you go back up here to when they occur, the degree has to be, and the numerator has to be larger than the degree of the denominator by exactly 1. So let's talk about the degree. The degree of the numerator is 2. The highest exponent is 2. The degree of the denominator is 1, because there's an imaginary 1 with that x. Okay, so yep, I'm bigger on top than I am on bottom by exactly 1, which means there is a slant asymptote. Okay, and so now we use synthetic division. And if you had a really good college algebra teacher, you probably remember synthetic division. But synthetic division, we are going to divide the numerator by the denominator. And so when you use synthetic division, if you're dividing by x plus 2, guys, you do not put a plus 2 in the box, you put a negative 2 in the box, because essentially you set the denominator equal to 0. Okay, so we put a negative 2 in our box. We then list the coefficients of the numerator. So the coefficients of the numerator are a 3, a 9, and a 1. Okay, and they're all positive, so I'm going to put a positive 3, a positive 9, and a positive 1. If you remember synthetic division, you bring down the first number. Hopefully this is ringing some bells for some of you. And then you multiply by the number in the box. So 3 times negative 2 is negative 6. 3 times negative 2 is negative 6. If you combine 9 and negative 6, you get a positive 3. 3 times negative 2, again, is a negative 6. If you combine 1 and negative 6, you get a negative 5. Okay? And so back in college algebra, negative 5 was your remainder. We're not really worried about the remainder. Think about it, guys. You were dividing a quadratic by linear. So this 3 does not actually represent 3. It represents 3x plus 3. Okay? So this answer right here is this. So if you're not sure about what I just did, you need to look up more videos on synthetic division. Okay? Because that is, like I said, a college algebra concept that should have been taught. But for this case, y equals 3x plus 3 is your slant asymptote. That is the slant asymptote. So the reason it's called slant, okay, here's my little corny joke for you, is because if you were to graph this, it would be up 3. Your y-intercept is 3, and then you could graph this. And so technically I should have graphed that as a dotted line, because that right there is your asymptote. So whereas up here, we had a vertical asymptote. Here, we had a vertical asymptote and a horizontal asymptote. Here, we have a slant asymptote because it literally has slope. Okay, so it's called a slant asymptote because it's slanted. However, sometimes, I'm glad this came up with my corny joke, because slant asymptotes are sometimes called oblique asymptotes. And I'm not sure what they call it on the PowerPoint, so make sure you know that slant asymptotes and oblique asymptotes are literally the same thing. Okay, so that's all the notes on